Welcome to CSI Training. Our mission is to impart the information, techniques, and the confidence you need to successfully apply RBM, reliability-based maintenance, its technologies and products. Thank you for joining the thousands who have recognized and selected CSI Training as the world leader for quality instructional products. This program will unveil the keys to successful diagnosis of rolling element bearing faults, employing spectral and waveform analysis. This is the first of a dynamic two-part series, destined to set the standard for rolling element bearing analysis and save millions of dollars in industry downtime. The second program focuses on determining severity, using the same data to answer the question everyone expects a precise answer to: how long will it last? Let's look at some of the physical characteristics of bearings to understand why we see the spectral and waveform patterns that we do. Each of these bearings has individual characteristics due to its own unique physical geometry, which cause specific frequencies to appear in spectral data when a defect is present. These defect frequencies can be calculated individually for the outer race, the inner race, the cage or fundamental train, and the balls or rollers. Let's take a look at how these can be approximated using an actual bearing on a shaft. The defect frequencies are often expressed as a multiple of the turning speed of the shaft. That is, for each revolution of the shaft, how many impacts will be made due to a particular fault. This bearing has been marked so we can visually determine the approximate frequencies. If a defect is at this position on the outer race, we can count how many balls will impact the defect during one revolution of the shaft. 1, 2, 3, 4, 5, and just a little more. 5 and a fraction balls impact the outer race with one revolution of the shaft. Notice that it is not exactly 5, but 5 and a fraction. This is the key to differentiating between bearing faults and other faults, such as vane pass, which would show up exactly 5 times for an impeller with 5 vanes. This fractional energy is called non-synchronous energy. That is, it is not a whole number multiple of the shaft turning speed, like 1.0, 2.0, or 3.0 orders. An order is a way of expressing frequency. Actually, there are 3 ways to express frequency: how often something occurs per minute or CPM, per second or hertz, per shaft revolution or orders. We will focus on orders because that is a direct correlation to shaft speed. The inner race frequency can be approximated in the same way as the outer race frequency. With the reference marks lined up again, we will assume a defect at the mark on the inner race. As the shaft is turned, let's count the number of balls that pass through the inner race defect. 1, 2, 3, 4, 5, 6, 7, 8, and a fraction. We see here that the inner race frequency is also non-synchronous. Notice that the inner race frequency is 8 and a fraction, whereas the outer race was 5 and a fraction. Unless the bearing is a unique thrust design with a 90-degree contact angle, the inner race frequency will always be a higher frequency than the outer race frequency. After lining up our reference marks, the cage frequency can also be approximated by rotating the shaft one full turn. With one complete revolution, we see that the cage went less than halfway around. Cage frequencies usually occur between 0.3 and 0.47 times the shaft turning speed. A defect on a roller will also generate certain discrete frequencies, depending on how many times the roller turns over during one revolution of the shaft. With the reference marks in line again, we rotate the shaft one full turn and this time count the revolutions of the roller. 1, 2, and a fraction. This roller defect frequency, or ball spin frequency as it is commonly called, is also non-synchronous energy. In our approximations, We've shown that the ball spin frequency, the outer race frequency, and the inner race frequency are all non-synchronous energy. The cage frequency is subsynchronous energy. That is, it rotates less than 1 time per shaft revolution. Therefore, a subsynchronous frequency is a lower frequency than shaft turning speed and is a fractional order value. The cage frequency will be less than 1/2 or 0.5 times turning speed, usually 0.3 to 0.47 times turning speed, except in that same rare occasion mentioned before, a 90-degree contact angle thrust bearing, or in an application where the inner race is stationary. All these frequencies can be determined exactly using FreakCal, the frequency calculation program in CSI's Master Trend software. This screen is the bearing calculation screen for inputting data about the bearing. A report is then generated showing the calculated frequencies for each component of the bearing. After entering the bearing name and number, 3 other fields are important. The first is the Use Physical Data field. Toggling this to Yes enables us to input the actual physical dimensions of the bearing. Secondly, specify whether the inner race is rotating. The frequencies are not the same in applications that have the outer race rotating. The frequency units can be toggled from Hertz to CPM to orders. We want to use orders so we can locate the bearing frequencies for any shaft speed. 4 pieces of information are needed for the frequency calculations. They are the number of balls or rollers, the diameter of the ball or roller, the pitch diameter, and the contact angle. The pitch diameter is the measurement across the bearing from the center lines of the balls or rollers. Tapered bearings are measured in the same way, through the center line of the rollers. The contact angle is 0 for bearings that do not have any thrust loading, such as this ball bearing. This angular contact ball bearing has a contact angle of 30 degrees. It is measured from the center line of the balls to the center of the curve. It is important to know the exact contact angle because the calculations vary with the angle. The contact angle and the pitch diameter are not readily available in the field. Often, the engineering group of the bearing manufacturer must be contacted for this information. Some manufacturers consider this information proprietary and will only give out the calculated frequencies. CSI has compiled a bearing file with nearly 16,000 common bearings that proves to be quite helpful in making an accurate diagnosis. This frequency calculation program can be a standalone product when used with a bearing file to perform the calculations. We are now ready to generate the calculated bearing frequencies. Notice that these frequencies are shown in orders, that is, multiples of turning speed of the shaft. A defective cage or fundamental train will show up at 0.38, which we expected because of the approximations made earlier. The ball spin frequency is 1.98. A defect on the outer race will show up at 4.19, and an inner race defect will show up at 6.81. The outer race and inner race frequencies added together will be a whole number equal to the number of balls or rollers in that bearing. When a manufacturer supplies only the calculated frequencies, CSI recommends always summing these inner and outer race frequency values to make a quick check that the data looks reasonable. Let's take a look at how some of the variables affect the calculated frequencies. If this bearing had been entered at 30 degrees instead of 5 degrees, how would the frequencies be changed? We see that the outer race and inner race frequencies are changed. They may not be much different, but when multiplied 4, 5, or 6 times, the difference really shows up. Later we will see why this is so important to us. Some machines have a bearing which is entirely for thrust. These have a contact angle of 90 degrees and are sometimes referred to as pancake bearings. We'll use the same bearing information, but change the contact angle to see the effect on the calculated frequencies. We see that the inner and outer race frequencies are the same, which we would expect since the races are the same. Notice that they still sum to equal the number of rolling elements. One question often asked is, when entering data for double row bearings, do you use the total number of rolling elements or just the number per row? Let's take a look at this double roll bearing and determine the answer. If there is a chip out of one side of this outer race, there will only be one row of rollers passing through the defect. Therefore, the frequency should be calculated based on the number of rolling elements in one row. These frequencies can be determined mathematically by inserting the bearing's physical data into some generic equations. The calculation in orders for the outer race frequency is shown here. In the equation, NB is the number of balls, BD is the ball diameter, PD is the pitch diameter, and theta is the contact angle. This is the equation for calculating the inner race. This equation is used to calculate the fundamental train frequency or cage. This final equation is used to determine the ball spin frequency. Remember that these equations give the frequencies in orders exhibited by defects in the individual components. However, it is also important to point out that if a specific bearing ID is not found in the file of nearly 16,000 entries, these formulas are resident in the FreakCal program of Master Trend to perform the calculations for you. This is a good time to address another common concern. Let's say that upon running a lookup for a particular bearing ID, many entries are located in the bearing file. Often, the entries are listed for various manufacturers, but can also be listed more than once for the same manufacturer. Though most of the bearings listed would be suitable replacements and can fit the shaft, the bearing design and therefore the physical geometry will be different. We have already determined that the physical geometry of the bearing determines the frequencies generated by defects in the various components, so it is important to know which bearing is actually in the machine. Approximations can be made for the race frequencies if the bearing ID and/or manufacturer is not known, but the number of rolling elements is known. The outer race is approximately 40% of the number of rolling elements, and the inner race frequency is approximately 60% of the number of rolling elements. Now let's consider bearing faults that can be detected using vibration analysis. Faults can be detected when there are defects on the inner or outer race, the rolling elements, or the cage. Other faults detectable by vibration analysis include looseness in the housing, excessive internal clearances, the bearing turning on the shaft, lack of lubrication, and a misaligned or cocked bearing. In spectral data, we expect to see peaks of some amplitude at 1 times turning speed due to unbalance, misalignment, or some amount of looseness. On gearboxes, we expect to see a peak at gear mesh frequency, which is the number of teeth times the turning speed of the shaft. On pumps or fans, we expect to see peaks related to vane pass or blade pass. The presence of these peaks does not necessarily indicate a problem or fault. However, bearing frequencies are defect frequencies, and their mere presence indicates at least an incipient problem and should send a warning to the analyst to pay attention. With a good bearing, these calculated defective component frequencies should not even appear. In a spectrum, it seems reasonable to expect the bearing frequencies to show up at their calculated defect frequencies. For the example bearing, a defective ball or roller would be at 2.4 orders. An outer race defect would be at 5.79 orders, and an inner race defect at 8.21 orders. However, these primary defect frequencies may be so low in amplitude that they are not even noticed by the analyst. Instead, it is multiples or harmonics of these defect frequencies that tend to show up first in the high-frequency range of the spectrum. Knowing this, we need to be very specific as to how we display spectral data. This spectrum is displayed in velocity, which allows us to see this high-frequency energy as well as the low frequency of 1 times and even subharmonics. When this same spectrum is displayed in displacement, all the high-frequency energy disappears. It may seem as if the machine is healed, but no mechanical change has occurred. Displacement amplifies the low-frequency energy and minimizes the higher frequencies. Displaying the same spectrum in acceleration now amplifies the high frequencies and minimizes the lower frequencies. This can cause you to overreact to this higher frequency data and at the same time ignore problems at 1, 2 and 3 times turning speed, which are often the problems that lead to premature bearing wear and failure. For this reason, we recommend that you view spectral data in velocity. Choosing not to compromise key root cause failure information at lower frequencies by selecting a velocity spectrum does not deny the value of acceleration data in the enhancement of high-frequency bearing defects. In this velocity spectrum from another machine, we can see how difficult it can be to discern a bearing defect because of the low amplitudes associated with these high frequencies. With the same spectrum and acceleration, we can also see why we would not necessarily want to collect the data in acceleration and miss the significant contributions due to the lower frequencies. We need the best of both worlds. Let's look at the time waveform in velocity and acceleration to determine its help in detecting high-frequency occurrences. Here we see a simple sinusoidal pattern at a frequency associated with a 1 times turning speed of the shaft. This velocity waveform is demonstrating significant unbalance on a fan and is very good information. But the velocity spectrum is similar, as expected. There is not much energy evident in the spectrum except unbalance. We're not able to change the unit's display of a singular time waveform after it has been collected. Instead, the data must be collected again using a different setup in the analyzer. When we display an acceleration time waveform from the same fan point, we see an underlying sinusoidal pattern. However, notice how significant the high-frequency information is displayed. Now we can see a tremendous amount of high-frequency data. The imbalance of this shaft is so significant that it is beginning to damage the fan bearings. As we develop the diagnosis for rolling element bearing defects in this program, we will derive tremendous value from acceleration time waveforms. Viewing data in acceleration clearly enhances the high frequencies, which is where the bearing defects occur. For these reasons, we strongly recommend storing the time waveforms in acceleration and the spectral data in velocity. With the Model 2115 machinery analyzer, this is accomplished in the change setup options. Select measurement mode and toggle the signal integration mode to digital. Using this setting along with an accelerometer, the waveform can be stored in Gs and the spectrum in velocity. This has the added benefit of viewing both the waveform and spectrum in their proper units while the data is still in the analyzer. First, let's consider several characteristics of outer race defects. This particular spectrum has a lot of high-frequency energy that is caused by the outer race of the bearing. Notice that these peaks are out of the high-frequency area of the spectrum. The primary or fundamental outer race frequency does not even appear. By marking one of these peaks and using the sideband cursor markers, we can move over to another peak. This change in frequency approximates the calculated outer race frequency, and the sideband cursors mark several of these peaks. The waveform for this spectrum has high energy levels in a repeatable pattern. Because the components are actually impacting each other, the amplitude in acceleration, or Gs, is high. Here again, we see that it is important to store the waveform in acceleration, even though the spectrum is stored in velocity. There is incredible impacting with up to 14 G peak-to-peak swing. Note the high levels as the rolling elements impact the defect and then smooth out on undamaged surface. This can be compared to an automobile tire impacting a pothole, coming back out and settling down as the pavement is smooth again. The historical spectral data for this bearing over the previous months looks like this. If we had been banking on the amplitude of the primary outer race frequency to show the severity, this bearing could have failed before an alarm was triggered. The second, third, and even fourth harmonic are negligible in amplitude. If we had collected the spectral data to only 20 times turning speed, we would have missed the bearing defect. Many analysts complain of missing bearings, and one key factor is they do not set the maximum frequency far enough out to see the defects. We need to realize, though, that small bearings with 7 or 8 rollers will probably begin showing up in frequency data at less than 35 times turning speed. On the other hand, Larger bearings with mini rollers will tend to show up first at much higher order frequencies. Although the next program in this series deals exclusively with determining severity of defects and how long the bearing will last,